So now that we know about aldehydes and ketones, let's talk a little bit more about the reactivity. Aldehydes and ketones pretty much react very similarly because they both have a carbonyl, but they're a little bit different still. For example, with an aldehyde, an oxidation can go to a C double bonded to the O, and then now we can have a CO bond that's new, H. On the other hand, ketones can't do this. Here's the reason why. A carbon-hydrogen bond can be interrupted. That's kind of okay to do. But keep in mind that this is a carbon-carbon bond on both sides. Not so easily done. And that's why a simple oxidation reaction is probably not going to work. But both of these can be reduced. By reducing each of them, what you're really doing is adding a hydrogen to both the carbon that's involved in that carbonyl and the oxygen that's involved in that carbonyl. And so that's why you get the hydrogen here and here, okay, and in both cases. Now be aware of the fact that this will look like a primary alcohol and this will look like a secondary alcohol, but the hydrogens that are on the carbon from the carbonyl will still be there. Looking at a couple of specific reactions that you probably should know also. The first is known as Tollin's test. And what you're doing here is you're using silver nitrate. Now silver nitrate has a silver +1 in there. And you're also using ammonia. And silver nitrate is a salt. It dissolves in water. It looks very, very much like water when it's dissolved. So you can't even tell that it's there. However, throughout this reaction, you actually end up getting silver with a 0 charge. So you actually get the silver metal that deposits itself. And this gives off a silver mirror. Now, what we're doing with this reagent is we're actually showing that this happened. So it's actually telling you, if you get this silver mirror, that this actually happened. And what this is the oxidation reaction of an aldehyde to a COOH. So that's a carboxylic acid, which we'll talk about later. Okay. So an aldehyde will give a positive Tollin's test that is a silver mirror. Similarly, Benedict's test uses copper sulfate. Copper sulfate will react only when you have an aldehyde with an OH next door. So there's a hydroxy that's right next to the C-double-O bond. What that does is it gives you two OHs, here and here, and then the copper sulfate is turned to C2O. Now this is a solid. It looks like red brick. So that's how you can tell if this has taken place. If you get this guy with a red brick color to it, that has taken place. Now here's the easy way to remember it. Silver is a precious metal and it makes you go, oh, that's pretty. And copper gives off a different red color that makes you go, oh, oh. That helps you remember it? Go for it. Okay. Just as a reminder, this is just the same thing we did on the last page. We've seen this before too, I think. If you have a C-double-O bond and you add an H2 catalyst, this is the same thing as a reduction. The hydrogen's going here and here, so you'll get that secondary alcohol. And here, if we have an aldehyde, hydrogen would go here and here, and you end up with a primary alcohol. This is sort of a tracing of where those hydrogens go. So we end up with one here on this carbon and one here there. So this is just a demonstration of what this looks like up here. If one of these, instead of being an R group or a carbon, is just a hydrogen, that's the difference between this and this right there. Okay. Now this gets a little bit more complicated. Acetals and hemiacetals. I'm going to start with this first line only for a reason, because that's really what you need to know. If we have, in this case, an aldehyde, and we're reacting it with any type of alcohol in the presence of an acid, what you get is that this oxygen right here will be attracted to this carbon. So you end up with a CO bond. And even though this is absolutely not the case, you can think of it as this hydrogen came from here. So that means you end up with an O, and this guy, minus his H, is connected to this, which is there. This now has an OH on it. That is known as a hemiacetal, or acetal. If you add more acid and more alcohol, then it will react a second time, and this OH will combine with this H, even though, again, that's wrong, but it will demonstrate my point. That sort of comes out as water. You end up with that oxygen on that same carbon there, and you end up with two of these that were originally alcohols. So if you want to think of it like this hydrogen from this alcohol, this hydrogen from this alcohol, and this oxygen right there make water. They leave behind just bat wings or whatever type of, thing you see there. You can do the same thing with a ketone. It doesn't change anything. This stuff that's down here stays the exact same. Notice that? This stayed the same. See? All that's changing is that carbon and that carbonyl, what's attached to it. Same thing here. This oxygen will go right there. See how that's the same thing? The only difference is this has a different R group instead of a hydrogen. So it has different carbons attached to it. Again, same thing. The only difference is the R versus the H. Okay. So let me give you an exact example here. Let's say that we started with this guy. I'm going to use a different alcohol. I want you to notice that this chain stays the same here and here. Now this oxygen is going to come to that carbonyl. And see how this makes that same bond? It's the same thing as up here, right? Okay. And on a second reaction, it's going to do two of them. Same thing as this. The only difference is we're now drawing out the carbons differently. And that's the only difference in these reactions. Okay? Practice this. This is definitely something you need to know. And here's why. An oxygen can react with itself in this case. So this would be a cyclic hemiacetal. Remember, it's easier for you to touch your own toe than for you to go down the hall, find somebody else, and touch their toe. So if a molecule can cyclize by itself, then it doesn't need to run into something else to react with. And that's exactly what's happening here. So in this case, the alcohol in this molecule can come and react there and give you a cyclic type of hemiacetal right there. I don't expect you to know this. I'm trying to expose you to it. So let's look at types of representations for glucose. This is something we're going to work with a lot next chapter. This would be one representation of that. One of those things about reaching down and touching your toes, you want to have a ring that's about 5, 6, or maybe 7 carbons in the ring. And so that's the reason why reactivity is as it is. And this one is the one that comes down here, not this one. Because here we get 1, 2, 3, 4, 5, 6. If we were to come over here, it would be 1, 2, 3, 4, 5, 6, 7. And so we kind of prefer 6-membered rings. And glucose, that's exactly what it does. Is that in another representation, this is known as the Fischer representation, which we'll talk about actually pretty soon. This oxygen can wrap up and react there. And so this is another representation of that. So if I kind of left this still and move this over, that's what this is doing. So see how that's wrapping around this way? Right there. Okay. We can represent this in the Fisher representation, which puts the C double O bond this way, and have all these OHs coming off, and see how many OHs we have in the ring. Another way to do that is as you see down here, which we'll talk about again next chapter, I believe. And that's how we end up getting this cycle. Now what this means is that the dark stuff that's coming towards you, that's supposed to be coming towards you exactly, and the other stuff is sort of in the back. That is the six-membered ring laying on its side. So instead of what you're used to seeing like this, that's what this looks like, flat. Down here we're doing this. Boom. So you can still see what's in the back. This is in the front, this is in the back. And so things that are closer to you, if they're darkened in, just like they are on the 3D type of thing. And this is very important when it comes to making carbohydrates, and we'll talk about that next chapter. Thank you very much.